Okay, good afternoon. So this is our 19th lecture, and today we will be having a bit short lecture. And now we will talk about ellipsoidal fluid particles. Okay, so as yes, I told you in the yesterday's lecture that once our Reynolds number is less than 600, then only spherical fluid particles can sustain, and once the Reynolds number is greater than 600, then there will be deformations in the shape of the fluid particles. So when we are going above then the 600 Reynolds number, and if we are having deformed shapes, then one of the common shapes which are obtained by fluid drops and bubbles is actually ellipsoidal shape. Okay, and in terms of ellipsoidal shape, because we have now complexity in terms of the geometrical configuration of the system, so that's why pure theoretical solutions are not exactly available. So in this case, we have to rely maximum on experimental and simulation data. Okay, so whatever the findings we will be discussing over here, these will be purely based on either experimental or simulation data. Okay, so theoretical approximations like boundary layer approximation, etc., are not applicable for this type of systems because of their complexity in the structure. So, one of the common system which we see in multi-phase systems is actually water and air. So we can see presence of water droplets in our surrounding air. So if we see in terms of the terminal velocity of a water drop present in air, and if we plot it as function of equivalent diameter. So over here, because the shape of the particle is not spherical, so that's why whenever we will be determining the diameter, that will be nothing but equivalent diameter. Now, equivalent diameter can be calculated based on multiple bases. So, the equivalent diameter which I am talking about over here, it is nothing but volume equivalent diameter. Is this point clear? So, this is our volume equivalent diameter. So, you can see when your diameter of the particle is increasing, then initially you have significant increase in the terminal velocity of the particle, but after some time, with significant increase in particle size, we will be having less increase in the terminal velocity. Okay, and one interesting observation you can see, we have also plotted Reynolds number over here, and the corresponding values of the Reynolds number for Reynolds number less than around 300. So for Reynolds number less than 300 and equivalent diameter less than 1 mm, we will be finding that in this range of diameter, our shape of droplet will be almost spherical. Okay, so in this range, this particular portion of the curve can be easily fitted by using the data of spherical fluid particles. Okay, and because this result is for water drop in air, so that's why this data can be even closely fitted with the outcome of the solid spheres, because we are talking about over here a water air system, and in case of water air system, value of K will be large. So if value of K is large, viscosity of the liquid droplet is large, in that case what we will be finding? We will be finding that there will not be presence of any internal circulations. So if internal circulations are not present, then this will be more closer to that of a solid sphere. Okay, and another interesting fact is the shape of particles remain almost ellipsoid in the range of 1 to 15, close to 1 to 10 mm. Okay, and after this size of equivalent diameter, if we go, then the drops which are of 10 mm or more size, corresponding to these drops, we will be finding that surface oscillations will be so large that particular drop cannot sustain as a single entity, that will be breaking into multiple other droplets. Okay, so that's why our range of diameter is actually less than the 10 mm. And second important outcome is, because I told you that only up to 1 mm we will be having the spherical shape, so other than 1 mm we will be having ellipsoidal shape. So by meaning of ellipsoidal shape is my droplet will be something like this. Okay, so typically you can see that if this is my axis of symmetry, this shape is nothing but a oblate ellipsoid. So if this is oblate ellipsoid, so aspect ratio will be less than 1. So that you can see here, this particular line is corresponding to the aspect ratio. So here you can see when you are having smaller diameter, then your aspect ratio is approaching to unity. When your diameter is increasing, your aspect ratio is actually decreasing. So it means shape is becoming more oblate, and which is like entering into the pure ellipsoid, for example. Is this point clear? Now you have this data of Reynolds number. So Reynolds number data can be fitted with this particular equation where we have ND over here, and we know from our previous lecture ND is called as best number, or it is also called as dimensionless equivalent diameter, and this particular ND can be calculated using this formulation. Okay, and this range of Reynolds number which is fitted over here, this is applicable for ND within the range 2.4 to 10 to power 7, and Reynolds number in the range of 0.1 to 3550. Okay, and similarly the data of this aspect ratio as a function of equivalent diameter can be fitted using this particular equation, and here this is applicable in the range of equivalent diameter 1 to 9. Okay. Then when we are talking about water air system, of course we have to talk about the drag force. Okay, so in terms of drag force, we can see that this thick black colored line is our standard drag curve. So standard, yes, this is for right hand side, means this is for aspect ratio depending upon each diameter. Yes, so that is what actually this data is only starting from this point. Okay, and before this point our diameter is less than 1 mm, so we are considering that it is almost a spherical shape and value will be close to 1. So you can see right hand side we have value as this value is 1. Okay, now the drag coefficient. So drag coefficient, this is a standard drag curve. So the meaning of standard drag curve is, this is drag curve for a spherical rigid body. Okay, and you have this particular curve for water drops in air. So you can see in the low Reynolds number cases, this water drops in air almost follows the same drag curve, but at larger Reynolds number it is actually having drag force higher in comparison to spherical. Why? Because at higher Reynolds number the shape is deforming and drop shape is getting flattened and it is becoming ellipsoid. So because of the ellipsoid shape it will be having more drag in comparison to the spherical objects. Okay, and then of course in this particular curve two more systems are discussed. So one is presence of bubbles in contaminated water, and second is presence of bubbles in pure water. So when you will be talking about the presence of bubbles in pure water, so typically bubbles are containing air fluid inside. Okay, so air or gaseous fluid inside. So typically gaseous fluid is having low viscosity, so K value will be small. So because of the small K value, for bubbles internal circulations will be predominant. So what internal circulations does, we know that for spherical objects internal circulations try to decrease the drag force. So that's why when I have pure system, in pure system it will be significantly dominant internal circulations. So that's why our drag coefficient is small, and after this point drag coefficient suddenly increases because after this point shape of the bubble changes from spherical to ellipsoid. Okay, and then in case of contaminated system, even if you have smaller Reynolds number, then also your internal circulations will be diminished. So that's why your value of drag is actually higher than the standard drag curve. Is this one clear?
Because of surfactant.
Yes, because of surfactant. So that is the contaminated system. Okay. Now, another interesting system is, in the previous system I have discussed the presence of liquid drops in air, particularly water drops in air, which was the large K system. Now I am talking about air bubble present in the water. So air bubble present in the system, here value of K is very small, approaching to 0. So when your value of K is very small, approaching to 0, so now it means that the effect of internal circulations will be predominant. In the previous case, because of the high viscosity of water, internal circulations were not much present. Okay, but here, because of the lower value of K, internal circulations will be significantly present in the system. So here you can see, when your equivalent diameter is very small, in the range of 0.55 or 0.66 mm, up to that you have almost linear increase in terminal velocity with diameter, because in this range, and also the corresponding value of Idvos number is also shown over here. So in this range our shape will be almost spherical. But after this point, for air bubbles you will be finding actually significant departure in the velocity values for different systems. So you can see some of the experimental data are following this particular curve, and some experimental data is following this particular curve. So now these two experimental data can be explained with the help of presence of contaminants in the system. So the experiments which are done with very pure system, so that no contaminant are present in the system. So for pure system, internal circulations will be dominant within the bubble. So once internal circulations are dominant, these will be having actually higher velocity, and after reaching a maximum velocity, then it will start decreasing and again. Okay, but in case of contaminated system, internal circulations will be diminished. So if internal circulations are diminished, these will be feeling more resistance. So that's why the corresponding values of terminal velocities are small. But one clear observation you can see, that this is the reason which is called as ellipsoidal regime, and in this ellipsoidal regime only we have significant differences in the pure system and the contaminated system. If I go before this regime, then my shape of the bubble is almost spherical. So that's why contaminated system and pure system are almost following a single curve. And whenever I go to very high value of the Reynolds number, corresponding to that again, the surface tension effect becomes so small that it is majorly dominated by the inertial effect of the flow. So that's why again after this point the contamination is actually not making much change, and the two curves are actually following the same data set. But in this particular range where we have the air system, so presence of contamination will be significantly controlling the internal circulation. So that's why we have different velocities. Is this point clear? Now, if we have to calculate the terminal velocity, maximum value of terminal velocity for the pure system, so this can be, terminal velocity in this particular regime can be calculated using this formula, and this formula will be applicable for all equivalent diameters greater than 1 point. Okay. So this distinction is clear to you. So one clear observation is, if you see a liquid drop, that will be almost showing the same velocity. It means there will be no effect of contamination on a liquid drop, because whatever contamination is doing, like it is stopping the internal circulation, that is already not present for a liquid drop because of its high viscosity. Okay, but for bubbles which are having low internal viscosity, for them contamination plays a significant role. Okay, then these are the air bubbles when these are traveling through water at 28.5 degrees Celsius. So depending upon the equivalent diameter, Reynolds number and aspect ratio, bubbles will be following different paths. Okay, so here these are having rectilinear path, it means these will be moving in a straight line. Then helical path, not straight but forming a helical structure. Then plane zigzag. In case of plane zigzag, there will not be any rotation like helix, but it will be only in a single plane, it will be oscillating like this. So if the range of diameter is like this, then you will be having plain, zigzag and helical. And then in this particular range you will be having simply plain zigzag, and then you will be having rectilinear with rocking. So rectilinear with rocking means it will be moving in a straight line, but in straight line only it can have jerk and oscillation in the vertical terms. Okay, so these are the different motions which you can experience in the experimental conditions, and how these motions will be actually affecting the wave formation, that we will discuss in the subsequent lecture. Okay, then whatever till now the cases I discussed, these were either air bubbles present in water or water drops present in air. But other than water and air, we can have other combinations of drops and other liquids and other gases present in the system. Okay, so if we try to consider the other drops and liquids, then one of the common curve which we have seen earlier also whenever I have categorized the shape of different bubble. So this curve is in between Reynolds number, Morton number and Idvos number. Okay, so other than the extreme values of gamma. So if you recall earlier also I told you that this particular curve was not applicable for extreme values. Other than extreme values, for all the intermediate values of k and gamma, you can take the help of this curve to determine shape and the corresponding values of velocity. Okay, because you are knowing Idvos number, Reynolds number and Morton number, so using these formulations you can actually, and you know also what fluid combinations you are having, basic fluid properties, so you can actually calculate the values of velocity. Okay. Now, for the other fluids, we will try to see that if we vary viscosity, then what will happen. So if you recall earlier also, I have concluded that whenever we talk about the motion of fluid particles present in a system, then majorly this motion is affected by only because of the viscosity of the surrounding fluid. Viscosity of fluid particle does not have much effect, okay, on the terminal velocity. So here, that is what's shown over here. So here, Reynolds number and Idvos number are presented for different experimental conditions, and in each of the experimental condition you can see different values of k were actually controlled. So k value is varied somewhere in the range of 0.35 to 19.8, and value of Morton number is varied from 2.0 to 2.2 into minus 10. Here also it is minus 10. Okay. So for very controlled range of Morton number, it means properties are not much changing much, but only viscosity is changing much. So here you can see these are the data of velocity, and almost this Idvos number and Reynolds number data is not showing any special trend upon variation of k, because here also you can see k is very high, 19.8, there it is 0.42, but there again high value of k 10.4. So it means viscosity ratio does not have any specific effect on the terminal velocity. Okay, so almost it is following a single curve. But if you talk about the presence of surface active contaminants, so the way I talked about presence of surface effective contaminants for air bubbles. So similarly here I am talking about different gas bubbles present in the different liquid mediums. Okay, so here you can see the similar effect, that for pure system you are having rise, and for contaminated system you are having lower values. Okay, so what you can do, this dashed line over here is nothing but fitted data, and this data of terminal velocity is for a pure system. So you can see for a pure system, terminal velocity can be simply written in terms of gamma, where what is gamma? Circulation factor, and k is viscosity ratio. So this entire curve can be fitted using this single equation for a pure system. If you have different liquid gas combinations, so different liquid gas combinations are accounted for in k. And for contaminated system, you have some dimensionless parameter j, which is given as Reynolds number into Morton number power 0.149 plus 0.857, and you have another non-dimensional parameter h, which is given as 4/3 with Bose number into Morton number minus 0.149 into viscosity ratios, viscosity of the continuous medium divided by viscosity of water minus 0.014. So these are two parameters, and these two parameters, if are fitted using this power law 3.42 into h power 0.441, particularly in the range of h from 2 to 59.3, then this can give the value of velocity for this contact. Okay, is this point clear? And all these field points are corresponding to experimental data, and open points are corresponding to simulation data. Is this point clear? And if you talk about in terms of effect of surfactants, because here we are saying that these two curves are slightly changing significantly. So surfactants has major effect that surfactants tend to damp out the internal motion, okay, by making the interface rigid. Second thing, the effect of surfactants will be most significant for low values of K, because for higher values of K, automatically viscosity is so high that internal circulation is not present, okay. And then surfactant have greatest influence on terminal velocity only near the transition phase from spherical to ellipsoidal, okay. And internal circulation can drastically alter the wake structure of a fluid particle, which can lead to delayed boundary layer separation, formation of small wake, and delayed vortex setting. That is something which we have discussed in the previous class as well. And also we have to remember one thing, that particularly the system for which value of surface tension is high, their surfactants actually plays major role, because for high sigma system, if you add surfactant, then their changes in surface tension will be significant, okay. And most experiments which are done in literature, these are almost grossly contaminated. In experiments, it is very difficult to maintain a pure, completely pure system. So there will be some sort of contamination present in the experiments, but this does not limit, this does not pose any limitation. Why? Because whenever you will be applying any gas liquid system for practical scenario, in practical scenario also there will be contamination. So it means whatever data you are obtaining from the contaminated experiments, same is going to applicable for the practical field situations. So that's why it does not make much change. Okay. And yeah, so it is difficult to eliminate contamination. Now whatever the I already told you that this is for contaminated system, these are the equations with the help of which we can mimic complete velocity profile, which I have shown earlier. Okay, so here you can see this first relation is applicable for h value from 2 to 59.3, and second relation is applicable for h value greater than 59.3. And of course, these j and h are nothing but some dimensionless parameters in terms of Bose number and Morton number. Okay, so ultimately we have to use these to calculate the value of terminal velocity. So from these relations, then terminal velocity can be calculated using this particular relation. Okay, so once you know the value of j and h, then you can calculate corresponding value of terminal velocity. Okay, so these relations are applicable for a contaminated system. So if you plot this data between j versus h curve, so you can see in next slide, this is my j versus h curve. So here you can see that the slope of this line is changing over here. Okay, so somewhere over here actually there is a change of slope. So this is nothing but transition limit of 59.3. So what you will be finding, before this transition limit of 59.3, you will be having a fixed shape of the interface and there will not be any interface oscillations. But after 59.3, in your ellipsoidal shape there will be presence of interface oscillations. And because of the interface oscillations, we will be experiencing enhancement of drag and decrease in the terminal velocity. So that is marked over here by this transition limit. Okay, so basically these equations are nothing but coming after fitting the data, and this has then come as the critical limit. And as I told you that for pure system, our terminal velocity can be given in terms of 1 plus circulation by 1 plus k. But how to calculate the value of circulation? So for circulation, once again, what is done, the circulation factor is plotted as function of Yudvos number into some function of viscosity ratio, and it was obtained that majority of the data is actually following this particular curve. So this curve can be used as a standard curve for calculation of vorticity, for calculation of circulation, and this circulation can be given as input to calculate the value of terminal velocity for a pure system. Okay, and of course this we have talked about the systems where contamination effect is dominant. It means we are talking about the systems for which value of K is small. So value of K is small, it means we are talking about presence of gas bubbles in liquid. On contrary, we can have other situation where contamination is not playing much role. It means presence of different liquid drops in air. So for presence of different liquid drops in air, you can see these are the series of equations which are fitted based on experimental or simulation data, and with the help of these equations actually you can calculate the value of terminal velocity. Okay, and this is one set of equations and this is another set of equation. So any of the equations you can actually use. These are nothing but all empirical correlations which are calculated for by doing data fitting over here. So here one clear difference you can see, that you can see over here, one is effect of K is not coming because K is large, so that's why circulation is not present, and also there is no effect of contamination because ultimately because of the large K, contaminants will not be affecting the circulation patterns. Okay, so this is the data for terminal velocity and drag coefficient for ellipsoidal bubble regime. In the next lecture, we will quickly discuss the different shapes of ellipsoid and what is the path of the ellipsoid. Today I have shown different paths. So how these paths actually affects the wake formation in case of ellipsoid fluid particles, that we will discuss in the next lecture. Okay. So now we will stop and